Hi there, folks. This is the Unit 9 review, and as always, I am the amazing Mr. Jansen. So away we go. If we take a look at the first one, when we're simplifying radicals, remember we have kind of two options for doing this. The first option is to look for perfect squares that divide evenly in this thing. So when I look at the square root of 99, I know that there's a perfect square of 9 that divides in. So the 99 is 9 times 11. And now I just take the square root of each perfect square. The square root of 9 is a 3. So I write that on the outside because I've taken the square root of it already. The 11 is still trapped. Okay? Same thing with the next one. I look for perfect squares that divide evenly into this thing. And so for this one, I know that it's divisible by 4, so this is 4 times 26. And now once again, I take the square root of each perfect square, so the square root of 4 is a 2, which I read on the outside. The 26 is still trapped, okay? This one, same thing. I'm looking for perfect squares that divide evenly into this guy. And the largest perfect square I see is 16, so it's 16 times 5. And then I take the square root of that guy. That gives me a 4. And the 5 is still trapped. And keep in mind, that's not the only perfect square that divides evenly into this one. You might do something like this, and you might end up kind of simplifying partially instead. Maybe you do something like 4 times 20, and then you say, okay, the square root of 4 is a 2, and the 20 is still trapped. And the thing about that is, this is a simplified version of the square root of 80, all right? But it's not completely simplified. We can keep simplifying that thing, because if you look at the 20, that's got a perfect square, and it's 4 times 5. The square root of 4 is a 2. So now on the outside I have 2 times 2, and then the square root of 5 is left, which is still 4 root 5. Okay, so just make sure you simplify all the way. That's not to say there's not more simplified version of this thing along the way, but typically we're looking for the most simplified version, okay? If I look at the next one, again, looking for perfect squares divide evenly into this thing. Maybe you see it, maybe you don't. If you don't see it, then you'll go to our other method. Remember, we have the other method of doing a factor tree to kind of fall back on. So this one's kind of a toss-up. Maybe you're going to see, oh, you know what, there's a 25 that goes in here, because maybe that's a little bit more obvious to you than it is to others. And then the square root of 25 is a 5, and that 7 is still trapped, okay? The other option here is to do a factor tree. If we start doing a factor tree, we just look for anything that divides in here. So maybe I do something like, I can tell that 5 goes in there because it ends with a 5. And when I do that, it leaves me with, let's see, that goes in 3, so 35 here. And then I can break the 35 up into a 7 and a 5. And then I circle pairs of numbers. I say, oh, look, there's a pair of 5s. So that comes out of the radical as a 5. And the thing that didn't have a pair stays inside the 7. Okay, so remember, those are our two options for simplifying this. We typically go to the factor tree when our other method becomes a little bit too cumbersome, or we can't find any perfect squares that divide evenly into that thing. Okay, for this next one, if you're lucky enough to realize that this one's already a perfect square, you can just go right to the answer of 18. But if not, this is where you might imply the other method, or maybe you'd look for perfect squares. But this one, you'd probably start breaking it down this way and say, oh, that's 2 times 162. And then you'd break that guy into a 2 times 81, and then maybe the 81 down into a 9 times a 9. And then you'd start taking the pairs and bringing them out. So you get a 2 on the outside, and you get a 9 on the outside, but there's nothing left on the inside, so that's how you get the 18, okay? So again, you kind of got to take these things as they come and say, all right, if I know any perfect squares divide evenly in here, I'll do that method. If I don't, maybe I'll do the factor tree. If I recognize a perfect square, then I'll take the square root of it, okay? So you kind of have to get a feel for these as you kind of look at the numbers, and sometimes it depends on how big or how small the number is, that kind of stuff, okay? Something like this guy, you might see that there's perfect squares divide evenly into here. Although seeing the largest perfect square is probably pretty difficult. That's 36 times 3. And then the square root of 36 is a 6. And the 3 is still trapped. You might be better off seeing something like the 4 that goes in here. Just because the thing ends in an 8, I don't know. I think that maybe is a little bit more obvious. If it's not, you go to something like a factor tree. That's cool. Factor trees are fine. So this one becomes this, but now I can break that 27 down into a 9 times 3, and I can keep going. So again, there are multiple simplified versions of this thing. We're just trying to work our way towards towards the most simplified, all right? And you'll get there faster by identifying the largest perfect square that divides evenly in there. But it's okay if you find a smaller one, okay? So again, keep that in mind as you're working through this thing. Like this guy right here, this answer of 2 square root of 27, that is a simplified version of this thing, but it's not the most simplified. So make sure you keep going, okay? If I look at the next one, we're doing the same kind of thing, but we just have a number kind of tagging along on the outside. So this one, it's going to be -3 square root. This guy, that's 4 times 13. And I'll show the little step in here, but you take the square root of the 4. So now on the outside, I have the -3. I now have a 2, and then the 13 still trapped, and now finish simplifying, -6 root 13. Okay? This one, again, if I look at this guy, that's a 144 times 2. The square root of 144, hold on, is a 12. So now on the outside, I have the 2 that was there. I now have a 12 out there as well. And the 2 is still trapped. And keep in mind, all of this is multiplication, so it remains multiplication after that thing gets out of that radical, okay? And now looking at something like variables. And remember, the variables, we want to divide the exponents by 2. If the exponent's not divisible by 2, we want to rewrite it as an exponent that's divisible by 2. So the 12 is fine. Y to the 17th, remember, we go closest without going over, so that's a 16. And then y to the first. And now again, as I take the square root, I divide the exponents. So remember, the square root of x to the 12th, I divide the exponent by 2, so that's an x to the 6th. The square root of y to the 16th is y to the 8th. Again, I'm dividing the exponent by 2, and then the y to the first is still trapped. Okay? The next one, I approach it the same way. I break the numbers down the way I always would. I break the variables down to get things that are divisible by 2. So this one, that would be a 9 times 7 for the perfect square of 9. The x to the 5th, I would break it down to the x to the 4th times x to the 1st. Remember, the closest number that's divisible by 4 without going over. So when we're talking about the 5, the closest one is a 4. And then it's y to the 8th. That one's already fine because it's already divisible by 2. So now I take the square root of 9. That's a 3. Let me write it down. I take the square root of this guy. When I do that, I divide the exponent by 2, so that's an x to the 2nd. This next variable, same thing. I divide the exponent by 2, so that's y to the 4th. And then trapped is the 7 and the x. Okay, so remember, the rule is when I'm taking the square root, I divide the exponent. Same thing with this guy. Let's break it down. So this one. Perfect squares divide evenly into 150. That's going to be a 25 times 6. And then closest without going over, that's a to the 8th, and then a to the 1st. The b, that's b to the 14th, and b to the 1st. And then the c to the 1st just stays the c to the 1st. There's not really anything I can do with that one at the moment. This 6 is still on the outside. That doesn't change. But now I start taking the square root. The square root of 25 is a 5, so I write that on the outside. Next, I take the square root of a to the 8th. That's a to the 4th. Remember, I divide the exponent by 2. The square root of b to the 14th is going to be a b to the 7th. I divide the exponent by 2. And now still trapped is the 6, the a b, and a c. And now I just have to clean up what's on the outside a little bit. The 5 and the 6 multiply to give me a 30. So it's 30 a to the 4th, b to the 7th, and then the square root of 6a, b, c. Okay? If I take a look at the next one, same kind of thing. That -4 is just going to kind of tag along for the ride. 48 is a 16 times 3. G to the 11th, closest without going over, is a 10. And then h to the 2nd is already divisible by 2. It's fine the way it is. The -4 keeps tagging along for the ride. Square root of 16 is a 4, so it joins this guy. The square root of g to the 10th, I divide the exponent by 2. That's g to the 5th. The square root of h to the 2nd, I divide the exponent by 2. That's an h to the 1st. and now still trapped is the 3 and the g, and now I clean it up a little bit. That's a negative 16 g to the 5th h square root of 3g. Next one, same kind of thing. I'm going to break it down. The 80, that's 16 times 5. 6 is already divisible. Y to the 13th closest without going over is a 12. Z to the 3rd closest without going over is a 2. And now I start taking the square root. Square root of 16 is a 4. The square root of x to the 6th, I divide the exponent by 2. That's an x to the 3rd. The square root of y to the 12th, I divide the exponent by 2. That's a y to the 6th. And then I still have that z hanging out over here. The square root of z to the 2nd, that's z to the 1st. Again, I'm dividing the exponents. And now I still have the 5, the y, and the z all trapped underneath there. And I'm done. Okay? If I take a look at the next one, remember, in order to add these things together, I need to have like radical terms, so they have to have the same radical with the same radicand. So it's got to be the same number underneath. So I can only combine two things that have the same radical portions, which are these guys. And so if I have a 6 root 5 minus an 8 root 5, I subtract the leading coefficients. So that's a negative 2. The root 5 stays the same. Okay, it had to be the same in order to add these together. It stays the same after I add or subtract. And then the minus 4 root 3 just tags along the ride. There's nothing else I can do there because those are not like radical terms. You can only combine like radical terms. Same thing with the next one. If I look at this guy, these guys are like radical terms. So I add those together. 3 plus 5 is an 8, so it's 8 root 2. And then the minus 4 root 3 just tags along for the ride. Okay? In the next one, I don't have any like radical terms yet, but I can simplify each of these radicals, so that's what I want to do. I want to simplify the radicals first to see if I end up with like radical terms. This is why it was important to simplify completely earlier, because if I don't simplify completely, I might miss out on something like radical terms. So here, that's the square root of each of these guys. So this one, the square root of 25 is a 5. When that comes out, 2 times the 5 is a 10. So I'm starting to cut out some of these little steps. Here, the square root of 4 is a 2. When that multiplies, that's also a 10. Here, the square root of 3 is or square root of 9 is a 3. When that comes out and multiplies, that gives me a 9 on the outside. And now I can see that the end two are like radical terms. These guys are both root 2's, so I can add those together. That gives me a 19 root 2, and then a minus 10 root 3. Okay? So I got to simplify first to see if I have like radical terms. Okay? If we look at the next one, again, I'm going to do the same kind of thing. I want to simplify this thing and then see if there's any like radical terms. So like on this one, I might say, okay, the 72 is 36 times 2. And if you need to take that off to the side because maybe you don't see that biggest perfect square of 36, that's okay. Take it off to the side and work it out. Here, the 8, that's 4 times 2. The 48, that's 16 times 3. And now I start simplifying each of these. And again, I'm going to cut out a little bit of the steps that I was doing before. But here, the square root of 36 is a 6 times 2 is the 12th. Here, the square root of 4 is a 2 times 2 is the 4. And here, the square root of 16 is a 4. And the 3 is still trapped. And so here, 2 of these are like radical terms, and 2 of them are the 1 is not. So these 2 are like radical terms. They have the same radical, the same radicand. So when I subtract these, that's an 8 root 2. And then the minus 4 root 3 kind of just tags along for the ride, okay? For these guys, remember when we're multiplying, the rule is outside times outside, inside times inside. When we have a binomial like this, we can FOIL or distribute here. So I'm going to distribute the 6 to each of these. And as I do that, I do outside times outside, inside times inside. That gives me a 12 minus 6 root 3. Again, I can't multiply the 6 and the 3 because one of them is outside the radical and one is inside the radical, and I have to keep those things separated. Okay? Now I'm going to distribute the negative root 3. Again, when I do this, it's going to be a negative 2 root 3. I can't multiply the 2 and the 3 because one's on the outside, one's on the inside. But then here, The negatives on the outside multiply to a positive, but inside it's 3 times 3, which is 9. And I'm allowed to multiply the 3's because they're both on the inside of the radical, okay? And then I simplify. The square root of 9 is actually a 3, so I can simplify that guy. These are like radical terms, so I can combine those. And then these terms on the outside, these are like terms as well. The 12 plus the 3 is a 15. So I end up with 15 minus 8 root 3. Okay. Next one is the same kind of thing. I'm going to FOIL or distribute here. So I'm going to distribute the 2 to each of these. And as I do that, it's outside times outside, inside times inside. So that's a 10 minus 2 root 2. And now I have to distribute the square root of 2 as well. That gives me a plus 5 root 2 and a minus root 4. I simplify the radicals as much as I can, so I see that square root of 4 over there. I'm going to simplify that to a 2. And now I'm going to combine like radical terms. I'm going to combine the like radical terms, the 2 in the middle. That's a 3 root 2. And now I can combine the terms on the outside. That's an 8 plus 3 root 2. Okay, so again, I distribute each of those outside times outside, inside times inside. I simplify the radicals. I combine like radical terms, and I combine the rest of the like terms as well. This one, same kind of thing. Lots of practice here. We haven't done some of these in a while. So I'm going to distribute each of those. As I distribute the 4, outside times outside, inside times inside, that's a 24 plus 4 root 5. And then I distribute the root 5. That's a plus 6 root 5. And then a plus square root of 25. Again, that's the case where I have inside times inside. And now I simplify. And now I have some like radical terms that I can combine. And then I can combine those terms on the outside as well. That's it. Next one, same kind of thing. This one's a little bit more difficult because I just have a little bit more going on, but I'm going to distribute that to root y. And again, outside times outside, inside times inside, that's a 6 root y minus a 2 root y squared. Okay, inside times inside. And now I have to distribute the square root of 3y. Again, outside times outside, inside times inside. So this one, again, I can't multiply those 3's because one's on the outside, one's on the inside, so I keep them separated like this. And then the last piece right here, outside times outside, inside times inside, gives me this guy. But now those square roots of y, the square roots of y squared, I can simplify those, this guy and this guy, because the square root of y squared is a y, so that becomes this. So it's 6 root y minus 2y with nothing left in the radical. And then here, that gives me a y on the outside, but a 3 is still trapped in the radical. And as I look across here, none of these are like radical terms. They kind of look like it because of like the square root of 3y and maybe the square root of y or the square root of 3. But everything under the radical has to be identical in order to combine these. So this one is done. There's nothing else I can do here. Okay. This guy, and I can already see that I forgot to change this example, so we'll cross that one out because these next two examples are the same. But again, I'm going to do the same thing. I should recognize that these are conjugates, and remember when I multiply conjugates, I know something special is going to happen. But I distribute the 6, that's a 36 minus 6 root 3. And now I distribute the square root of 3, that's a plus 6 root 3, and a minus square root of 9. And now I simplify the same way I've been simplifying. These middle terms, when I combine them, are actually opposites, so they cancel out. So all I'm left with is 36 minus 3, which is just a 33. Remember, that was the special thing that happened with conjugates, is when I multiply conjugates, the middle term cancels. But more importantly, with radicals, when I multiply by conjugates, all the radical terms go away. Okay. This guy, same kind of thing. Remember, when you're squaring this thing, that's like doing that guy times itself. So you have to do 2 plus root 5 times 2 plus root 5. And now you have to use your distributive property from here, okay? So here I'm going to distribute the 2. That gives me a 4 plus 2 root 5. And then I'm going to distribute the root 5. That gives me a plus 2 root 5 plus 20 square root of 25. And now I simplify. And you can combine some of these steps. I'm just showing all of them. And then I combine the like radical terms. And then I combine the rest of the terms. This one, same kind of thing. You got to write it twice. So it's 8 minus root 2 times 8 minus root 2. And so now here I distribute this guy. And then I'm going to distribute this guy. And as I do that, I get a 64 minus 8 root 2 minus 8 root 2 minus the square root of 4. I simplify. I combine the like radical terms. And be careful here. These are both negative, so they're not going to cancel. They're actually going to give me a negative 16 root 2. And now I finish combining the rest of these terms. That's a 62 minus 16 root 2. Okay? For these guys, rationalize the denominator. Remember, when we have just a single term down there, I have to multiply by that thing by itself to get rid of it. So I'm going to multiply by root 5, but whatever I do to the denominator, I have to do to the numerator. Okay? Now the same rules of multiplication apply. It's outside times outside, inside times inside. So that gives me 6 root 10. Down here, that gives me the square root of 25. And now I simplify. The square root of 25 is a 5. And then I reduce the fraction if I can. I can't reduce this one. I can't reduce the 10 and the 5 because one's inside the radical and one's outside the radical. Remember, we have to keep those things separated, okay? This one, same kind of thing. I have to multiply that root 2 by itself, so I have to multiply by the square root of 2. Whatever I do to the denominator, I have to do to the numerator. And so now here's the thing. That numerator, I have to use my distributive property here in order to multiply those two things. So again, I still do the outside times outside, inside times inside. 2 root 2 plus the square root of 12. But now I have to keep simplifying down here, the square root of 4. So that's 2 root 2 plus the square root of 12. If you take it off to the side, 12 is 4 times 3. The square root of 4 is a 2, and the 3 is still trapped. And that's just simplifying like we did on the first page of this review, like we've been simplifying. And if you need to take that off to the side, go ahead and do that. And down here I get a 2, but now I can use my distributive property to do some division. Notice all the outside numbers are divisible by 2. So this becomes a root 2 plus root 3 if I divide each of those exterior numbers. Okay? Down here, when you have a binomial in the denominator, the only way to eliminate all the radicals is to multiply by the conjugate. So this one, instead of root 5 plus root 2, I'm going to multiply by root 5 minus root 2. And whatever I do to the denominator, I have to do to the numerator. And so now in the numerator, once again, that is my distributive property. In the denominator, take it off to the side if you need to. So here, the numerator, I'll go 9 root 5 minus 9 root 2. But the denominator, let me take that off to the side and do it. And that's what's going to be most beneficial for most of you, is to take it off to the side. Some of you are going to be really good at this, and you can go ahead and multiply it right as it is, where it is. But I'm going to take it over here and do my distributive property. That's the square root of 25 minus the square root of 10. And now distribute the next piece. That's plus the square root of 10, and then a minus square root of 4. The middle terms, once again, cancel, and I can simplify. So I simplify, that's a 5 minus a 2, which is a 3. So that's my denominator. And now reduce the whole fraction. Notice all those outside numbers are divisible by 3. If I use my distributive property, that's 3 root 5 minus 3 root 2. That's it. If I look at this guy, again, same thing. I want to multiply by the conjugate. So I have to multiply by 4 plus root 3. Whatever I do to the denominator, I have to do to the numerator. And now let's take these off to the side. There's a lot going on here. So let's take them off to the side and do the multiplication. So in the numerator, I have this. And I'm going to use my distributive property. So I'm going to simplify this the way I've been simplifying these things. So I distribute that 3. Outside times outside, inside times inside. And I distribute the negative root 3. And now I continue to simplify. The middle terms combined. That's a negative 1 root 3. This guy becomes a minus 3. I combine more of the terms. That's a 9 minus root 3. So that's my numerator. I still have to do the denominator. And again, take it off to the side. Don't take any chances here. I distribute the 4. I'm not going to show the arcs this time. Ready? 16 plus 4 root 3. Whoa, I need to draw those arcs, Mr. Jansen. And I'll distribute the negative root 3. That's a minus 4 root 3 and a minus root 9. But see, as you get used to these, as you get really good at these, here the middle terms cancel. You can start to cut out some of those steps. Okay? And that's it. This one doesn't simplify any further. But again, take them off to the side, do your multiplication, and go from there. Okay? If I look at this next one, so now we're solving. Remember, solving, we're working backwards sort of operations. But keep in mind, the thing under the square root is technically in parentheses. So this guy's technically in parentheses, which means I undo it last. So here I undo addition and subtraction first. So I'm going to add the 6 to each side. And now I'm going to divide by that 4. And now I'm going to undo the radical. I'm going to undo the square root by squaring each side. Remember, roots and exponents are inverse operations. So I square each side. That cancels out with the radical, so I'm left with x plus 5. Over here I get a 16, and now I subtract. And the other thing you have to remember is you got to make sure that you plug these back in and check them with these, because we will get extraneous solutions from time to time. Remember, extraneous solutions are solutions that look like they should be right, but they still don't work when you plug them in. They're wrong because of the situation, not because of the work you did. Okay? So if you get an extraneous solution, you did everything right, but it still doesn't work when you plug it back in. Okay? So plug that one back in, you'll see that it does work. Okay? This one, same kind of thing. Remember, we add this guy over to the other side. So I'm undoing order of operations. Now I divide each side by the 3. I'm now going to undo the square root by squaring each side. And now I can divide each side by the 3. And it looks like I get the answer x equals 4/3, which is what I should get because I've done everything correctly. But that answer is still wrong. This is an extraneous solution. And I know it's an extraneous solution by actually plugging it back in and seeing if it works. So if I actually plug this guy back in, ready? 3 times 4/3 under there, and then minus 2. And let's see if it equals the negative 8. So here, that times that is a 4. The square root of 4 is a 2. So that's 6 minus 2. And 6 minus 2 is a 4. So I get 4 equals negative 8. And there's two possible reasons why I would not get the right answer when I plug this thing back in. Either I messed something up, or the situation is impossible. And that's the case here. I did everything right, but this answer is still wrong. X does not equal this thing. That's an extraneous solution. So there are no valid answers. So the answer here is no solution. Okay? Just solving a couple more of these. Again, make sure you plug them back in when you're done. But we're working backwards through root of operations. So here I subtract the 3 from each side. And then I divide by the negative 2. Now to undo the square root, I square each side. and then I divide by the 5. And again, I'm going to get an answer here, but I have to check that answer. Plug it back in and check it. This one works when you plug it back in, okay? The next one, same kind of thing. I'm working backwards sort of operation, so I'm going to add that 4 over to the other side. I undo everything outside the radical first because, again, inside the radical, that 3x minus 2 is technically in parentheses. So before I can undo that stuff, I have to get rid of everything around it. So I'm going to square each side to get rid of that square root. And now I'm going to finish solving. Add that 2 to each side. And now I'm going to divide each side by 3. Oops, sorry, that is a 66. Crazy Mr. Jansen. So I end up with x equals, looks like a 22. And again, plug it back in, make sure that it works. This one does when I plug it back in. This guy, I've already got the radical isolated on each side. Just go right to squaring it. Get rid of that square root by squaring each side. And now simplify. Subtract the x from each side. Remember, you got to get your variables on the same side first. And now finish solving. Add that 5 over to the other side. And divide by the 2. And this one, again, you got to plug it back in and check it. So I get the x equals 4. This one's a little bit trickier to plug back in, but if you plug it into this side, 4 plus 3 is a 7, so you get the square root of 7. Over on the other side, 3 times 4 is a 12, minus 5 is a 7, so I also get the square root of 7. It doesn't matter that I can't simplify that any further. It's okay that it's in radical form as long as I get the same thing on each side of the equation. So x equals 4, that one does work, okay? And then this one, let's square each side. So here I get a 2x minus 8 equals a 4 minus x. Once again, I'm going to get the x's on the same side first because that's how I solve equations typically. So I'm going to add that x over. And now I'm going to add that 8 to the other side. And then divide by the 3. And once again, I'm going to have to plug this thing back in and check it. If I plug it into that first side, I have 2 times 4 is an 8. Minus 8 is a 0. And the square root of 0 is a 0. Over on this side, 4 minus 4 is a 0. The square root of 0 is also a 0, so that one does work. I do get the same thing on each side. So again, remember, check for extraneous solutions. Extraneous solutions basically did everything right, but the answer is still wrong, all right? And so if you want to explain that in your own words here, you could explain it using my words that I've just used. They're when you've done everything right, but that answer still doesn't work. It's because the situation is impossible, not because of anything that you did. Okay, extraneous solutions are the trickiest ones to identify. See, it's easy to go back and look for mistakes in your work, but if there are no mistakes in your work and the answer still doesn't work, it's an extraneous solution. Okay, it's because the equation in some way has a restriction on it that makes it impossible. Okay.